Welcome back. We are going to be covering 13.1 today, which is the first official section of chapter 13 in our textbook, dealing with right triangle trigonometry. So, what is trigonometry? You've probably heard that word a lot. Trigonometry, or trig for short, has to do with triangles. The study between the relationship, I guess, between angles and sides of triangles. Again, metry, kind of looking at the measures of a triangle, trigonometry. And so right here on the screen, I have a quick diagram of a right triangle. We know it's a right triangle because of the little box indicating that those two sides intersect in a perpendicular manner, 90 degrees. And then over here in the bottom right, I have a symbol which you may or may not be familiar with. This is the Greek letter theta. Theta is kind of a zero with a little slash through it. That's what I got on OneNote anyway, as close as we can get there. And so what we're looking at here is an angle that we usually use as kind of our basis for our conversations. Theta, kind of like we always use x for side lengths or missing values in algebra. Theta is often used for the missing angle, an unknown angle. And really, in theory, it looks a little bit more like this. But again, OneNote, that's the theta that I had available to me when making this. So I've labeled each of these sides with really important names. The hypotenuse is the one we're probably most familiar with. It's across from the 90-degree angle. So the hypotenuse is that long, often thought of as a diagonal. But the other two are kind of interchangeable sometimes, and it all depends on where theta is. In this diagram, the longer leg is called the opposite leg because it's opposite the triangle from theta. And the other leg will be called the adjacent leg because adjacent is a word that means next to or touching or right near. And so this leg is really near theta, our angle that we're looking at. And this leg is opposite theta. But it all depends on where theta is. For example, if theta in red were up here, well, then the opposite would be down below and the adjacent would be next to it on the left, right? So it's all dependent on which angle we're looking at where theta is. But if we know these three sides, these names of these three sides, we can define 6 trig functions for right triangles that you are going to need to know. And so scrolling down, and I will talk about all this, but I would love for you to pause the video and take just a few seconds writing down those 6 trig ratios. Sine, cosine, tangent on the top row, cosecant, secant, cotangent on the bottom row in green. And then for good measure, also jot down what I have highlighted in yellow there. Cosecant, secant, cotangent, alternate definitions. So I'm going to pause my video, you do the same, and then once you're done, unpause it. All right, let's talk about these trig ratios. Starting in the top left in green, sine of theta. So sine is a trig function that simply describes the opposite leg over the hypotenuse and how they compare. Is one larger than the other? Well, the hypotenuse should always be larger because the hypotenuse is the longest side of a right triangle. But how much larger? Is it twice as big? Is it 10 times as big? We're going to use sine theta to really determine that relationship between those two sides, as you will see here on numerous examples. The second one, cos, stands for cosine. And I'll write the names out. I know they're in the description above, but we've got sine, we've got cosine describing the relationship between the adjacent leg and the hypotenuse. We've got tangent, which is spelled as it sounds, tangent, E-N-T, which then describes the opposite and the adjacent. How do they compare? Now, what about cosecant? Cosecant is really just sine flipped on its head, if you look. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. They're basically just reciprocals of each other. Then we have secant. And we have cotangent. And so secant is the reciprocal of cosine, hypotenuse over adjacent, and cotangent is the reciprocal of tangent, adjacent over hypotenuse. Now, as we're starting out this unit, keep this section of your notes handy. You'll be looking at it probably a lot until you have it memorized, and you will have it memorized. I mean, we are going to do a lot with these concepts. So make sure you have this handy for reference. Also worth noting, especially for calculator work, cosecant can also be described as 1 over sine, because again, it's that reciprocal of sine. So 1 over sine, copy dot flip, just flips sine. Secant is 1 divided by cosine, cotangent is 1 divided by tangent of theta. All right. Now, there is probably something that might be in the back of your brain saying, I think we've studied this before. We talked about it a different way. You might be thinking of SOHCAHTOA. All right. SOHCAHTOA is a device that we often use to remember these, at least the top row here, of trig functions. I've also seen it written, and I kind of like it written like this. So, ka, toa. And really what this is, again, is just a device for our brains to remember that, oh, so sine theta equals the opposite over the hypotenuse. And that's what this says right here, or when they're all written in a row. It's the order how we write them. Sine theta is the opposite over the hypotenuse. Change colors of my highlighter. Blue, cosine is equal to the adjacent side over the hypotenuse. And then finally, I'll go orange for this, I guess. That was a bad idea. Red and orange don't contrast well, so I'll go light purple. TOA, tan theta, is equal to opposite over, adjacent for tangent. Opposite over adjacent, so TOA. So if you've heard those, I mean, I'm going to be using that word, that phrase, throughout this whole unit. And so that's what I'm referring to. Just remembering, okay, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So SOHCAHTOA. Well, the first thing that we're gonna then be able to do with triangles is we want to be able to write out these ratios of these trig functions. So looking at this triangle, bringing a little bit of geometry knowledge in here, remember that angles are typically referred to and labeled with capital letters. So you can see we have triangle DEF, and so each of those vertices, those vertexes, is labeled with a capital letter. And off to the right here, I'm asking for those 6 trig functions, all with regard to angle D. D is kind of my theta right now. D is my point of reference where the whole conversation starts, because that's what it's asked for here. Sine of D, cosine of D, tangent of D, secant, cosecant, cotangent of D. So here's where we stand with this. If we're looking from angle D, first thing I want to do, just to make life easy on myself, is label these sides. That's the opposite side. It's across the triangle. It's opposite the triangle from my angle D. This is going to be my adjacent leg, the one that's part of the right angle that's right next to angle D. And then across from my 90 degree will be my hypotenuse, 35. Now, why do I like to label these? Because now it makes my job really easy. I know that sine is opposite over hypotenuse. So katoa. So that means that sine of D is just going to be 21, my opposite side, over 35. Because I've already labeled those opposite hypotenuse, 21 over 35, which, as we should always do, as we are in the habit of doing, we can simplify this ratio, this fraction, divide them both by 7, 3 over 5. So sine of angle D equals 3 over 5. That means that the opposite side is 3/5 as long as the hypotenuse. That's that description. It's a little bit more than half the length of the hypotenuse. What about cosine? So cosine is adjacent over hypotenuse. So we're looking at 28 over 35 from my diagram, which again, both divisible by 7, 4/5. So the adjacent side is 4/5, is 80% as long as my hypotenuse. Let's do tangent, so katoa, so opposite over adjacent, make a slightly better A there. The opposite side was 21, the adjacent side was 28. Divide them both by 7 to simplify the fraction, 3/4. Tangent equals 3/4. Now, I could go through the same exercise for the next 3. I could say secant. Okay, so that was hypotenuse over adjacent. If you look at your notes, secant is hypotenuse over adjacent. And so that's 35 over 28. Divide them both by 7 is 5/4. But hopefully you're seeing, oh, there's a quicker way to do this. I know that secant is just cosine flipped. So instead of 4/5, which I got for cosine, I'm going to say 5/4 for secant. Cosecant is just sine flip, so I can go straight to 5/3. And cotangent, tangent are reciprocals. I'll just go straight to 4/3. So this is the first kind of problem that you're going to be seeing that you need to know how to handle. Can you list out these trig function values just by grabbing these side lengths and those ratios? So what I would like you to do is do the exact same problem just with some different numbers. You'll notice that now there's a theta in there, again a one-note theta we'll call it. So everything is from G. So let's start this together. That means this would be my opposite side because it's across opposite the triangle. This will be my my adjacent side up here. And then across from the right angle is the hypotenuse. Life looks good until you realize, wait a second, I'm missing one of those sides. And it's not a special right triangle. It's not one of those 30-60-90s or 45-45-90s we saw in 13.0. How do we find this missing side length for the adjacent leg? Well, remember that it's a right triangle, and so we can definitely do something along the lines of Pythagorean theorem, a squared plus b squared equals c squared. So really in this triangle, I'm gonna hit you with a little bit more geometry review. This is side lowercase h because it's across from angle h. Angles are denoted with capital letters. The side across from the angle is the exact same letter but lowercase. So that's h. I can rewrite this probably as h squared plus, looks like g squared equals f squared. So h squared plus g was 10 squared, the length of that side, equals 12 squared. H squared equals plus 100 is equal to 144, meaning h squared equals 144 and I lied, 44, subtract the 100, sorry. If you can't tell, I'm pretty tired right now. So right there, square root both of them. This is 4 and 11, 2 and 2. So h equals 2 root 11 in this problem, obtained from the Pythagorean theorem, 2 root 11. Okay, pause the video, list out your 6 trig functions. Make sure that you do whatever you got to do to make sure you don't have a radical on bottom. If that root 11 ends up in the denominator, fix it, right? Rationalize the denominator. I'm going to pause mine, work it out, and we'll compare answers in just a second. All right, here's what I got for my 6 trig functions. You can see the work I did to rationalize some denominators, make sure the root 11s weren't down there. But first, sine theta, I just got 5/6. 10 over 12 simplified to 5/6. And immediately then, you didn't see it because it was paused, but I just went down and filled in cosecant. 6/5, just the reciprocal. Similar with cosine. Cosine 2 root 11 over 12, so root 11 over 6. And then I just immediately filled in secant. I did have to rationalize that denominator, but 6 root 11 over 11. And then finally, on tangent, once I multiplied by root 11 top and bottom, I got 5 root 11 over 11, which then I can just flip for cotangent, came out to be root 11 over 5. So hopefully you got those same values. If not, check, see if our work differed somewhere. If you have a question, make sure to bring that up. So this is kind of the first thing we need to do. We need to know these trig ratios, these trig functions, and be able to list them out like this. But that's not the main thing we're going to do, which is good because that's kind of tedious. The main thing we're going to do is going to be solving triangles, sometimes with these special angle measurements, 30, 45, and 60, finding sines and cosines and tangents and cosecants and secants and cotangents. Sometimes they'll have any value for an angle, any measurement. We are eventually going to be memorizing each of these, okay? Each of these values in this table. You can see I grabbed this table from your book. You can tell from the distinctive color scheme. One thing I want to point out and make sure you see, there was a giant typo in your book. I'm not sure how this passed quality control, but the 30-degree row for tangent, they had listed as root 3 over 2. That is very much not true. That is very much not true at all. And so root 3 over 3, sorry, that 3 is a little bit better. Root 3 over 3 is the tangent value for 30 degrees. Everything else looked good, but this was kind of a major mistake on their part when they published this book. We are going to memorize these, and I'm going to be showing you a couple ways that really make it easy so that you're not just having to literally memorize with no context. But I'm hoping you see some patterns, such as 30 degrees sine and cosine are flipped from 60 degrees sine and cosine. 45 sine and cosine are the same, and there are more patterns, and you can tell them. And one thing I'm hoping you might recognize and notice from our 13.0 lesson is all of these values come from those special right triangles when the hypotenuse is 1. I mentioned that's a very, very, very special important case in math, in trigonometry. So where that short length in the 30, 60, 90 is 1/2 and the longer leg is root 3 over 2, you start seeing those values in the 30 degree and 60 degree rows, 1/2 root 3 over 2. Similarly, in the 45, 45, 90 row, root 2 over 2 is a big player, and you can see that kind of in the 45 degree row. So nothing to do right now with this, but I just wanted you to be aware we will be going through this and memorizing all of these values and more. So before we get to kind of the last 1.5 skills for this lesson, I need you to pull out your calculator and make sure it's in the right mode for the following problems. So what you want to do is on these TI calculators, if you have one, the button placement should be pretty similar to mine. If not, your button might be somewhere else. But right up here, you can see where I'm pressing. Hopefully you can see sine, cosine, tangent. I'm going to clear that out. But we have those 3 buttons. I want you to press tan, type in 45, and then hit enter. If it gives you a value of 1, you are good to go. You are in degree mode. And so you are ready for these next problems. If yours gives you 1.619775191, like mine does, we need to just change your mode really quickly. It's currently in a different setting for measuring angles, something called radians. And we're actually going to talk about that in 13.2, what radians are and how they work. But for now, you need to change your mode. So on these TI calculators, you're going to hit the mode button right next to second, the blue one. And then you can see on mine the 3rd one down. It's usually the 3rd or 4th row down. You can see where it says radian and radian is highlighted. I'm going to go down. I'm going to go right to degree, and I'm going to hit enter. And now degree should be highlighted, putting this in degree mode. If I go second quit and say tan 45 now, missed the tan button, tan 45. Now it says 1. Now I know I'm good to go for these problems. Otherwise, I'll be typing in everything right, doing all the right math, and my calculator will tell me the wrong answer. Not ideal. So make sure that your tan 45 equals 1. All right. So here is what we are going to be doing the rest of this section is finding a missing value of a triangle, a right triangle. So quick 3-step process. Identify which trig function applies, sine, cosine, tangent. Write an equation using that trig function, and then solve for your missing value using a calculator. Let me show you what that means here. I am given, other than the right angle, I am given one angle here. It's this 30 degrees. So with regard to this 30-degree angle, I'm looking at what 2 sides are kind of in play on this problem. Over here, I've got the opposite side. That's what I'm looking for. And what side do I know? I know my adjacent leg. So it's all based on which angle I'm given. 30 degrees, I'm looking for the opposite. I have the adjacent. So which of my 3 main trig functions uses the opposite and the adjacent? And as you can see, I'm writing out SOHCAHTOA. Opposite, adjacent, that looks like a job for TOA, tangent. So here's what you're going to do. Tan of theta equals opposite over adjacent. We know that. That's our starting equation for tangent. Well, then let's start plugging things in. Tan of 30 degrees is my angle, equals the opposite side, which is x, over the adjacent side, which is 10. And then we know how to get x alone here. I'm going to multiply by 10 on both sides. So 10 times tangent of 30 degrees equals x. And that's something I can now plug in my calculator. That's why we grabbed our calculators. 10 tangent of 30 degrees, 5.77-ish. In this class, we keep 4 decimal points, round to the 4th decimal point for precision. And so x, we will say, is 5.7735 in this problem. X equals 5.7735. Now, before I scroll away from this problem, I like to just think to myself, does that make sense? I mean, judging by the picture, judging by what I know that small sides are across from small angles, 5.7, almost 6, does that look about right? Does that seem right? The answer is yes. If that's 10, I could see that being just about 6. It can save you just that quick little check, a lot of hassle and headache of a silly mistake. So get in the habit of doing that. How about right here? 60 degrees, 3x. So First thing I would do, I would come down here. I'd say, well, I know this is my hypotenuse. It's across from the 90-degree angle. And this is my adjacent side. It's right next to my angle. So which of my three main trig functions uses adjacent and hypotenuse? Looks like a job for cosine this time. So we can write our cosine equation. I know that cosine of theta equals adjacent over hypotenuse. So I'll replace some things. Cosine of 60 degrees equals adjacent is 3 over x, the hypotenuse. Now, looking at this, what I want you to see is, okay, x is on bottom this time. That's a little more problematic, but not too much. I'm going to show you the two-step process, and then I'm going to talk about some things switching places, and then probably the rest of the way I'll just talk about things switching places because I think that's easier. I want to get x out of the denominator. I'm going to multiply by x on both sides. So x times cosine of 60 degrees equals 3. And then to get x alone, I can just divide by cosine of 60 degrees. And x equals 3 over cosine of 60 degrees. Now, before I plug that in my calculator, let's talk about the little switcheroo that happened. Up here in the line that I am starring right now, we had cosine 60 degrees equals 3 over x. Now, if x is on bottom, this is typically how it's going to play out. We multiply the x up to the other side, and we divide the trig function, divide the cosine 60 down. Notice how, from our original, cosine 60 and x just switched places when all was said and done. The x came up to the other side, the cosine 60 divided by down. So that's kind of how I will think about it. I'll probably on future problems say, okay, multiply the x up, divide the cosine 60 down, and hopefully you will know what that means. So x equals 3 over cosine of 60 degrees. Pop out my calculator. 3 divided by cosine of 60. X equals 6. Does that look reasonable? I could see it. I mean, never trust a picture completely, but this is the hypotenuse. It should be the longest side. So if that adjacent side is 3, I could see this being 6. Yeah, that seems reasonable. All right. I would like you to try something. I would like you to solve for 3 values on this triangle. Challenge yourself a little bit, see if you can do it. I would like you to find side length F. I would like you to find side length H, and I would like you to find the measurement of angle H. Now you might be saying, I don't know how to find the measurement of an angle. Think about what all the interior angles in a triangle need to add up to. So think about that, look at those measurements given, sketch this out, do a couple trig problems to find those missing side lengths, and then unpause the video and I will work it out a little bit quickly, but I will work it out in front of you as well. All right, let's do this. You had a chance to work and try to find those 3 values. The lowercase h, the side length h, the side length f, and then the angle for angle h, the measurement of that angle. I'm going to start with that last one because I know that the 3 angles inside of a triangle have to add up to 180. So I can come down here and say, I know that there's a 7 degree, I know that there's a 90 degree, plus h have to add up to 180 degrees. And a little bit of quick arithmetic tell me that h equals 20 degrees. Okay, so just using that fact that all triangles, interior angles, add up to 180 degrees, not too hard to find h. Cool. How do we find the other 2 side lengths? Because I'm given 18. Well, now I can use those trig skills that we were talking about before. And And the cool thing is I can use either 20 or 70 as my angle point of reference, my anchor, if you will. I'm going to use 70 just because it was given to me. There's no rhyme or reason, really. I mean, I could use either one here. But I'm going to use 70, and I'm going to first solve for h. So from 70, this is my opposite side. This is my adjacent side. So opposite, adjacent, so TOA. I know that tan theta equals opposite over adjacent. And so I can say tan 70 degrees equals the opposite side was 18 over the adjacent side, which is h. Now here's where I'm going to say, multiply that h up, divide that tan 70 down. That'll leave me with h equals 18 over tan 70. Visualize that happening in your mind. H multiplies up, tan divides down. And so now it's just a question for the calculator saying, what is 18 divided by tan 70 degrees? 6.5515 if we round that 4 up because of the 6 after it. So 6.5515. H equals 6.5515. Does that look realistic? I mean, it looks a little bit small from the picture, but again, never trust a picture. I know that it's across from the 20-degree side. The 20-degree is really small, a small angle, so we should get a pretty small side compared to the 18. 6 seems reasonable. Now let's find f. F is my hypotenuse in this problem. So I might look at opposite hypotenuse. So is sine of theta equals the opposite over the hypotenuse. So sine of 70 degrees equals 18 over f. Same game, right? Multiply the f up, divide the sine 70 down. F will equal 18 divided by sine 70. F equals 18 divided by sine 70. 19.1552 when we round that fourth decimal. 19.1552. Not that much longer than my longer leg. But it is longer, which is good because it's the hypotenuse. It needs to be the longest side length. So 19.1552, that seems reasonable. This is how we can find missing side lengths using trigonometry in these right triangles. Knowing the SOHCAHTOA, identifying which trig function should we use here, writing an equation, and then solving for your missing value. Fundamental foundational skill that you have to have. So take a good look at this and really make sure you feel good about these problems. Now, there are 3 more problems, fairly quick problems that we'll be doing in this video. I know there's a lot in this video, but we also have what are called inverse trig functions. We're still going to be using the calculator for them. Inverse, sine with a little -1 up there. Inverse sine, or inverse cosine, or inverse tan are normal trig functions with a little -1 up there. You will also see them and hear them referred to as arc sine. That's the exact same as inverse sine. Arc cosine is the exact same as inverse cosine. Arc tan is the exact same as inverse tan. So just know that they have 2 names. Arc means inverse in this case. Now, we use the regular trig functions to solve for missing side lengths. All is good, good for us. What if we're missing an angle? That's when we're going to use the inverse of our trig functions. Let me demonstrate. Right here, right triangle, I know that that left-hand leg is 13. The hypotenuse is 22. I'm looking for x. I'm trying to figure out how many degrees is this? Well, I know that this is my opposite side, opposite my angle. And this is the hypotenuse. So if that's true, then let's start this the exact same way we started the previous three problems when we were looking for side lengths. So that means, so Katoa, I'm going to use sine. Sine of theta equals opposite over hypotenuse. So sine of x degrees equals 13 over 22. Let me tell you what we don't do. We do not divide by sine. That's the number one incorrect answer, if you will, when we're trying to find for x here. We can't divide by sine. Sine is a function. It's not a value, a number we can divide by. But we do need to get rid of it somehow. We do need to get that x broken out of the sine function. And how we're going to do that is by inverse sining both sides. Because what do you think on that left-hand side? Inverse sine, sine inverse of sine does, they cancel each other out. And so we're going to be left with x degrees equals inverse sine of 13 over 22. And that's where we can pop over to our calculator. If you hit the second functionality and then press sine, right above sine, you should see a little sign with a -1. Inverse sine of 13 over 22, 36. Now for angles, because 1 degree is so tiny, we typically just round to the nearest degree. Side lengths, 4 decimal places, but angles, we're just going to round to the nearest degree. So 36, x is equal to 36. X degrees we can say is 36 degrees there. All right. So pretty much the same process, but now we're finding missing angles with those inverse trig functions. What about this one? Yeah, there's a radical, who cares? Let's just do this one. We have angle theta. Looks like we're dealing with opposite and adjacent. So Katoa. So we know that tan theta equals opposite over adjacent. So tan theta equals root 15 over 7. And then here's the other way you can think of it. What I showed earlier is the proper way. What's happening mathematically? We take the tan inverse of both sides, and that gets rid of the tan. Sometimes people say, how can I get the tan over to the other side? Well, what's the opposite of tan? Tan inverse. So like moving that tan to the other side makes it tan inverse. And that's how sometimes people like to think of it. Now, is that mathematically precise? No. But if it's easier for you to understand what's happening there, I'm okay with you thinking of it that way. Theta equals tan inverse of root 15 over 7, meaning theta equals, there's that inverse tan, root 15 divided by 7. 29 degrees if we round to the nearest degree. 29 degrees. Okay, so inverse trig functions being used here to find missing angles. But we set up the equation the exact same way. Last problem. This calls for a word problem. Because I know how much everyone loves word problems. Bridge construction. In order to construct a bridge, the width of the river must be determined. Suppose a stake is planted on one side of the river directly across from a second stake on the opposite side. At a distance of 50 meters to the left of the stake, an angle of 82 degrees is measured between the two stakes. Find the width of the river. This is kind of a complicated problem to wrap your head around until you realize that we were given a picture. Look over here. says it's not drawn to scale, but it sure kind of helps us out, at least visualize this. Here's a stake. Here's a stake, 50 meters to the left. It forms an 82-degree angle. If I hadn't wrapped this up as a word problem and had just given you this picture, it would have been exactly the same as those other problems we were working. So yes, word problems can be tricky to translate into a picture, into an equation, but really the math stays exactly the same. Let's do this. 82 degrees. So we have opposite is W. We've got adjacent is 50. I want you to set up an equation, solve it, and see if I know the picture's not drawn to scale, but we should get a pretty big number for the width of that river because it's across from an 82-degree angle. It's a pretty big angle. Pause it. I'm going to pause it, work it out. We'll compare answers in just a second. All right, my final answer, 355.7685 meters is the width of our river. You can see I set up my tan equation, tan theta equals the opposite side over the adjacent. So W over 50, multiply by 50 on both sides, plug it in your calculator, and get around 356 meters. So everything we've talked about today, not true. Most everything we've talked about today, you saw in geometry. Not the cosecant, secant, and cotangent necessarily, but sine, cosine, tangent, SOHCAHTOA, how to find those missing sides, how to find those missing angles, you probably have seen before. Here's the difference. In geometry, typically, we spend like 2 weeks going over it. We just spent one video, one long, packed video, but one video. And you need to be really good at this. This is actually one of the most useful things for the question everyone asks, when am I going to use this in everyday life? Use this a lot. Think about looking for an angle. Let's say you're trying to figure out what angle should you build your, what lengths of wood should you use to build your staircase? Because the stairs, the city planner says the stairs need to have an angle of elevation of 4 degrees or 8 degrees. Well, then you need to be able to figure out how high and what's the diagonal, what's that actual step, the horizontal, what should those be? If you're building a deck in your backyard, a lot of times you'll be using these calculations to find missing side lengths, missing angle measures of these triangles. So really, really, please take a look at these practice problems. And if you usually after doing practice problems feel like, okay, I'm probably like a 7 out of 10 at that understanding wise, I would love for you to be at least a 9 for these concepts, because these are really good things to know, important things to know. And if that means doing a couple extra problems or coming in for help, asking questions, do it. Watch a YouTube video, rewatch this video, but these are really important skills. 13.1, a packed section, a lot to it. Thank you guys for sticking with me. Take a look at your practice problems. If you have questions, definitely bring them up next time I see you. Other than that, have a great day, and I will see you in 13.2.